Welcome back, pre-calc friends. This is AP Calculus section 2.4 notes. Today we're going to be talking about continuity of a function. And in calculus, continuity has a three-part definition. Three things are required for a function f to be continuous at some point a. Those three criteria are, number one, f of a has to be defined. That is, when you plug in whatever a is, like if a is 2, when you plug in x equals 2, then that value has to be in the domain of the function, and f of a has to be a number. It has to exist. It can't not exist on our graph. The second criteria is that the limit as x approaches a of our function exists. And the third criteria is that the limit as x approaches a of our function is equal to the value of the function. Meaning, we can't have a hole at a or a vertical asymptote at a. When x is a, that has to be part of the continuous function. When we think of continuity just in terms of a graph, I often think of what we call the lift the pencil test. For a graph to be continuous on a given interval means that as you trace the graph, and right now I can trace this curve, I never have to lift my pencil up. And if you can say that that is the case as you are tracing a graph, that it passes the lift the pencil test, then you can say that that function is continuous on that interval. When we look at example 1, we're given a graph, and it says, part A, from the graph of f, state the numbers at which f is discontinuous and explain why. When we look at our graph, we have several locations, first of all, where we can see that there are discontinuities in our graph. One of them occurs right here at x equals -4. You can see that there is a hole there. We have another discontinuity at x equals -2. We have one at x equals +2, and we have one at x equals +4. So for example 1, part A, it says state the numbers at which f is discontinuous and explain why. So x equals -4, the graph is discontinuous, and that's because there's a hole there. So I'm going to switch colors. That green's a little hard to read here. At x equals -4, we would say that f is undefined, right? Because we have a hole in the graph at x equals 4. At x equals -2, we're discontinuous. At x equals +2 and at x equals 4. And the reason that we are discontinuous at these three locations is the same for all of them. And that reason is that the limit does not exist in those locations because for all three of those x values, the left-hand limit and the right-hand limit do not agree. So we can say limit does not exist because the left-hand limit does not equal the right-hand limit, and that's the case for all three of those. Then part B says, for each of the numbers stated in part A, so x equals -4, x equals -2, +2, and 4, determine whether f is continuous from the right or from the left or neither. Okay, so part B, at x equals -4, it's a neither, because in order for it to be continuous from the right or continuous from the left, then there has to be a closed circle at A. Because the x value -4 has an open circle, we have to say that it's not continuous from the left-hand side or from the right-hand side of -4. At x equals -2, we can say that our function is continuous from the left. Only from left, right? Because we have this closed circle right there. So from the left, we could say our graph is continuous, but not from the right because we have an open circle coming from the right. At x equals 2, +2, we have a similar situation. We have a closed circle here and we have an open circle here. So we can say that as we approach 2 from the right, we are continuous. So continuous only from the right. And then finally, at x equals 4, same idea. We have a closed circle. It looks like there's probably, I don't know, some sort of an asymptote going on here at 4 because this side just is plunging downward over here. But we can say that we are continuous from the right-hand side only. So I think this graph really helps us understand continuity, why things are not continuous, looking at a graph, and then understanding what it means to be continuous from one side, continuous from the left or continuous from the right, that you need to have a closed circle in order for that to be the case. Example 2, we are given 2 different functions, and we are supposed to explain where and why they would have discontinuities and what type of discontinuities those graphs would have. So for the first one, I think that the easiest thing to do, since we have a polynomial in the numerator and a polynomial in the denominator, is to try to factor. If I factor my numerator, that's just an easy factor. That's going to factor into x plus 5 times x minus 2. And then I have that family of x minus 2 on the bottom. Now we've seen this enough times already this year that hopefully you've committed this to memory. Whenever we have the same family appearing in our numerator and our denominator, that creates a hole in the graph. So for the first one, we would say f of x has a, and the formal name for a hole is a removable discontinuity, which is a hole, at x equals positive 2, because that's the value that would make those families x minus 2 equal 0. So we have a removable discontinuity. If you were to graph this function, remember, it would look like a straight line, a y equals mx plus b equation with a y-intercept of 5 and a slope of 1, but on that diagonal line, at the point where x is positive 2, there would be that tiny little hole in the graph because that point does not exist. In the second function, we have f of x equals x squared over x plus 1. No factoring required here, but in our denominator, you can see that we have this family of x plus 1. And we said in a previous set of notes that if we have a family only occurring in the denominator, that this creates a vertical asymptote at that location. And a vertical asymptote's formal name is an infinite discontinuity. So we would say f of x has an infinite discontinuity, which we call a vertical asymptote at x equals negative 1. Continuing on, we have this kind of table of information here that talks about continuity, just some more information. The first 2 things have to do with continuous from the right or continuous from the left, which we already talked about a little bit when we looked at that graph in example 1. But this is just reiterating here that a function f is continuous from the right if, as x approaches a from the right, f of x is equal to f of a, meaning we have to have that closed circle at x equals a in order for the graph to be continuous from the right. It might stop at that point and not live on the left side, but it could still be considered continuous from the right. And then the exact opposite would be continuous from the left. We'd have to have that closed circle as we approached x equals a from the left. A function f is continuous on a given interval if it is continuous at every number in the interval. There's our lift the pencil test. If you're given an interval between x equals something and x equals something, and you can take your pencil and you can trace the graph from point A to point B and never lift your pencil, you can say that that function f is continuous on that interval. And at the endpoints of those intervals, we would understand that we would be discussing continuity as being continuous from the left or from the right only because we're looking at an endpoint of the interval. And then we have our functions here, our combined functions, addition, subtraction, multiplication, and division. Basically, if f and g are both continuous at some value a, then all of these combinations of functions are also continuous at a. A polynomial is continuous everywhere because its domain is all reals. So every polynomial should pass a lift the pencil test because they are always all continuous everywhere. Rational functions are continuous wherever they are defined. So if you take the time to do the domain work and determine the domain of a rational function, it will be continuous everywhere in that domain. And then if f is continuous at b and the limit, this just is talking about our limits of functions and understanding that a composition of functions, kind of below it says, if g is continuous at a and f is continuous at g of a, then the composition f of g of a is continuous at x equals a. A continuous function of a continuous function is a continuous function. All right, so using all that information, and there's a lot there, you're going to be kind of referring back to that table now and again as you think about continuity. Let's take a look at our next few examples. Example 3 says, explain why the function is discontinuous at the given value a equals 1 and sketch a graph of the function. Well, first of all, f of x is a piecewise function, right? Because we've got that it is equal to x squared minus x over x squared minus 1 if our values of x are not equal to 1. And then our function is equal to 1 if x is equal to 1. Well, the first thing I'm going to do is I'm just going to kind of pick apart my function a little bit, and I'm going to factor the polynomial part of my function, or the rational part of my function. I'm going to factor the polynomial in the numerator and in the denominator. So in the numerator, I can factor out an x, and in the denominator, that's a difference of squares. So when I do that, hopefully, the first thing that you notice right away is that I've got this family of x minus 1 upstairs and downstairs, and I've got this family of x plus 1 only downstairs. So based on what I already know, I can say that f of x will be discontinuous at x equals 1, and that's because we will have a hole there, and at x equals negative 1, and that's because we will have a vertical asymptote there. Okay, so that kind of answers why the function is discontinuous. Now they want us to sketch a graph. So I am going to build a little coordinate plane. And I'm also going to make a table to complete my graph. I'm just going to look at my fave 5 here for graphing purposes. All right, so as I start plugging in x values, when x is negative 2, and I plug negative 2 into my function, that's going to be, everything is going to be for values of x that are not equal to 1, except when I plug in 1, right? So when I plug in negative 2, and I do the math, negative 2 squared minus negative 2 divided by negative 2 squared minus 1, that's going to give me a result of 1. When I plug in negative 1, I know that I am undefined because that creates 0 in my denominator. When I plug in 0, I get 0. Now, when I plug in 1, I know that that actually gives me a value of 1/2, but I want to remind you that there's actually going to be a hole there because that point does not really exist on our curve. And then when x is 2, we have a value of 2/3. So we can go ahead, and these are just, I got these from plugging them in, and really I know that when x is 1, the function is 1. I do have that point 1, 1. That's that removable discontinuity, or that whole spot in my graph. So now I'm just going to plot my points, and we'll take a look at what we have. When x is -2, y is 1. When x is -1, y is undefined. And that's because I have a vertical asymptote there. When x is 0, y is 0. When x is 1, y is 1/2, but it's not a point, it's a whole. When x is 2, I get 2/3. All right, and so basically, I know what this looks like because it's a rational function, and I know that it's going to have a branch that goes up like this. And I don't know if you remember back from pre-calculus the rules of horizontal asymptotes, but the rules of horizontal asymptotes state that when your numerator and your denominator have the same degree, which in this case they do, we have x squared over x squared, that the horizontal asymptote is a ratio of your leading coefficients. Well, the leading coefficient of the numerator is a 1, and the leading coefficient of the denominator is 1, which tells me that I have a horizontal asymptote at y equals 1. And so the branch on this side of my curve is going to look something like this, and it's going to stay under that horizontal asymptote. So this is kind of a picture of what my graph looks like. I have that removable discontinuity, but then I know that the actual value of my function when x equals 1 is 1. So then I do have this closed dot sitting right there, kind of that oddball spot. That's what makes this a piecewise function. And I have a good picture here of my discontinuities in graph form, but I also have an explanation of my discontinuities in equation form. In example 4, we're asked to explain why the function is continuous at every number in its domain and then state the domain. R of x is equal to x squared plus the square root of 2x minus 1. The part of the function that we need to be concerned with when we think about domain is the square root of 2x minus 1, because we have an even root. So we would say that our domain for this function would have to be that x has to be a number, that 2x minus 1 has to be a number greater than or equal to 0, because we have to keep what's underneath that radical 0 or bigger. So then if I solve this for x, I get that x has to be greater than or equal to 1/2, which would give us a domain of 1/2 comma infinity. And it says, state the domain, but also explain why it's continuous at every number in its domain. Well, this goes back to that information about continuity in the box above. So by the definition of continuity, a root function is continuous at every number in its domain. Example 5 says, show that f is continuous on -infinity to +infinity. Well, we are given the function f of x, and we can see that this is a piecewise function. We've got one piece of our function being x squared, which we know is a polynomial. Specifically, it's a parabola. And that's for values of x that are less than 1. So right now, I'm just going to sketch a picture of what this looks like, because I can easily graph y equals x squared. That's simply going to be a parabola but only on the left side of 1. So I'm going to go ahead and I'm going to draw that yellow line there where x equals 1. And if it's for values of x that are less than 1, that means that where my parabola would intersect 1, right there, I need to have an open circle. So here's the left-hand side of my piecewise function. Then on the right-hand side, where x is greater than or equal to 1, I have the square root of x, which I know the square root of x looks kind of like a sideways parabola, just the top half of it. So it starts at 0, 0. That's its first point. However, that's not going to be in the domain of the function because it's for values of x that are greater than or equal to 1. The next point would be 1, 1. So the next point would be right there. And then I'd have a point at 4, 2. And if I continued, I'd have a point at 9, 3, so on and so forth. So you can see that where the open circle of x squared is lying, we have a closed circle for the square root of x to show that this graph is continuous. And again, quick check, let's do our lift the pencil test. If we were to trace our graph, we never have to lift our pencil. We can continue to trace the entire graph from negative infinity to positive infinity. So it is continuous. This is a way that we can show it with a graph or graphically, but we could also show this algebraically, because if f of x is continuous everywhere, then when x equals 1, x squared should equal the square root of x. That should be true, right? Well, when I plug 1 in, I get 1 squared is equal to the square root of 1. On the left side, I get 1. On the right side, I get 1, which is a true statement. 1 does equal 1. So we showed that f of x is continuous everywhere, both graphically and algebraically. Example 6 asks us, for what value of the constant c is the function f continuous on the interval negative infinity to infinity? So again, we have another piecewise function, and our domain change is happening when x equals 2. So what they are asking us to do in this problem is, when x equals 2, what does c have to be for the two functions to equal each other at that location in order for us to have continuity? We need them to meet at the point x equals 2. So we would have to figure out what would our c value have to be in order for this to happen. Okay, so this is the question we're trying to answer. When x is 2, what does c have to be in order for these two equations to equal each other so that they meet at that point and our function is continuous? So this is what we have to show, that cx squared plus 2x is equal to x cubed minus cx when x is 2. So I'm going to go ahead and I'm going to plug 2 in for x, and I'm going to solve for c and figure out what c value would make this happen. So c times 2 squared plus 2 times 2 is equal to 2 cubed minus c times 2. And then I simplify. 2 squared is 4, so I get 4c plus 4 is equal to 2 cubed is 8 minus 2c. If I get my c terms on the same side, I'm going to add 2c to both sides, and I get 6c, and then I will subtract 4, get my constants on the other side, so 6c is equal to 4. When I divide by 6, I can reduce 4/6, and my answer is 2/3. So for c equals 2/3, this function will be continuous. The first function is a parabola, the second function is a snake, and they will meet at the same point when x is 2. Now we're going to change gears a little bit, and we're going to discuss the Intermediate Value Theorem, which is a very big theorem in calculus. And it's not hard to understand, and I think the picture really helps us see clearly what we're talking about here. The intermediate value theorem says that suppose f is continuous, and that is really important. Okay, if we're applying the intermediate value theorem, f has to be continuous on the interval that we're looking at, passing the lift the pencil test. Then n is any number that is between the interval x equals a and x equals b, so n would be some number between f of a and f of b. There has to exist some number c in my interval a to b such that f of c is equal to n. So basically, in layman's terms, the intermediate value theorem says that a continuous function is going to take on every intermediate value between the function values f of a and f of b. And this should make sense. Let's take a look at the pictures here that sort of illustrate this for us. First of all, please notice that in the first picture, our function f of x is continuous. It passes the lift the pencil test. Okay, so we have a continuous function. We have two values along the x-axis, a and b. And graphically, we can see where f of a is on our function, and we can see where f of b is on our function. And the intermediate value theorem says that there has to be some value c that lives between a and b, so here's c, such that f of c is equal to n, and n is a number between f of a and f of b. So that makes sense, right? If the function is continuous, there has to be a value c that produces an output of n, and n has to live somewhere between the output that you get when you plug in a and the output that you get when you plug in b. And you can see that in the picture. The second picture just shows you another situation where our function is still continuous. We just have a different c value this time. And so you can see that in this case, we have two c values where our function has an output value of n in between a and b. Same idea, two different illustrations of the intermediate value theorem. Example 7 says, show that there is a root of the given equation in the specified interval, a by the intermediate value theorem, and b graphically. So the first thing that we're going to do is the graphically part, okay? I'm going to do part b first. So part b, I'm going to go ahead and I'm going to sketch a graph of what this function looks like on the interval x equals 1 to x equals 2. All right, so I'm just going to plot a few points here, okay? And when I plot a few points, I'm just going to make a table. I'm going to do my fave 5, -2, -1, 0, 1, and 2. And I'm just plugging these right into x squared plus x minus 3. So when I plug in -2, -2 squared is 4. 4 plus -2 is 2. 2 minus 3 is -1. When I plug in -1, -1 squared is 1. 1 plus -1 is 0. 0 minus 3 is -3. When I plug in 0, I get -3. When I plug in 1, 1 squared is 1, plus 1 is 2. 2 minus 3 is -1. And when I plug in 2, 2 squared is 4. 4 plus 2 is 6. 6 minus 3 is 3. All right, so I have some points that I can plot here. -2, -1, -1, -3, 0, -3, 1, -1, and +2, +3. Okay, so what this tells me, based on the symmetry of my table, is that my vertex has to lie right in here between -1 and 0. And so if I want to figure out what my vertex is, obviously if it's right between -1 and 0, the x value of my vertex has to have a value of negative 0.5. So if I take negative 0.5 and I square it, I add negative 0.5, and then I subtract 3, I get a value of negative 3.25. So my vertex is going to be at negative 3.25, which is about right there. So I can go ahead and I can sketch a picture of what this parabola looks like. Sorry, it's a little sloppy, but you get the idea. All right, so I was supposed to show that there is a root of the given equation in the specified interval, and I chose to do part B first, which is to show that this is true graphically. Well, right here, you can see, right in my picture, here is x equals 1, here is x equals 2, and you can see that I have a root or an x-intercept on my curve that lives between those two values. Now, how do I show this using the intermediate value theorem? Okay, well, f of 1, I already did, that's in my table, but f of 1 is equal to 1 squared plus 1 minus 3, which gives me a value of negative 1. F of 2 is equal to 2 squared plus 2 minus 3, which gave me a value of positive 3. Okay? So if I am going to use the intermediate value theorem to prove that there is a root, I would say, a little bit of writing here, the function is a polynomial and thus continuous everywhere, or continuous on negative infinity to positive infinity. Since f of 1 equals negative 1 and f of 2 equals positive 3, and the function changes from negative to positive, right? Negative 1, when x is 1, we get negative 1, so it's negative. When x is 2, we get positive 3, so it's positive. So when the function changes from negative to positive on the interval 1 to 2, by the intermediate value theorem, it must cross the x-axis and therefore have a root in the interval 1 to 2. Okay, so this is our part A right here. Whenever we use a theorem in calculus, we always have to be able to back up our explanation with words. We have to be able to explain the math in words. So make sure that you understand the words that we just wrote down and how that is an explanation of why there is a root between x equals 1 and x equals 2, citing the intermediate value theorem. Our final example for this set of notes asks us to use our graphing device to find the root of the following equation correct to 3 decimal places. And it says, note, there are 2 ways that you can do this. We've already done a similar problem to this in a previous lesson. So let's review. Our first way, before we grab our calculators, is we could set this equation equal to 0. We could get everything on the same side of the equal sign. We could graph it on our graphing calculator, plug it into y equals, and then step 3 would be to find the x-intercept, okay, which would be second level, calculate 0. Okay, that's the first way. The second way, and my preferred way, would be to graph both equations. And then step 2 would be to find the intersection, right? Because if we want to know where does the square root of x minus 2 equal 1 over x minus 1, that's going to be where those two graphs cross each other. And that's going to be second level, calculate, intersect. All right, so right now I am going to do the second way. So I'm going to grab my graphing calculator. I'm going to go into y equals. If you have something there, clear it out, and we're going to type in our two equations. So the first equation is going to be the square root of x minus 2. Square root is a second level function above x squared, so square root of, and then x minus 2. Okay, and then I'm going to arrow out from under my radical. I'm going to arrow down to y2, and that's going to be 1 divided by, now I have to parenthesize my denominator, so I have to put x minus 1 in parentheses. And then I am just going to do a zoom 6 on this, standard window. All right, so you can see the red graph is the 1 over x minus 1. That's a rational function that is just shifted 1 unit to the right. And then our square root of x minus 2 is a standard square root graph that is shifted 2 units to the right. But what we're interested in looking at this graph is where do these two lines intersect each other, okay? So again, now we're going to go to second level, calculate, and then number 5 is intersect. And this is where we have to do the first curve, second curve. So right now, looking for my cursor, but they are on, right now they are on the y1, which is the blue curve. And there it is. It doesn't exist until x equals 2, so I had to move it a little bit. So yes, this is my first curve. I'm going to hit enter. Then it pops the cursor down to the red curve and it says, is this the second curve? Yes, enter. And now do we want to make a guess on the intersection? Yes, we do. Hit enter. And there it is. Our intersection is at x equals 2.4655712 with a y value of 0.6823278. Whew, lots of decimal places there. Remember that when we are seeking an intersection point, or we're seeking a root, or we're seeking a solution, it's always the x value of the ordered pair that we are looking for. So let's go back to our page here and let's sketch a picture of what this graph looked like. Doesn't have to be anything fancy, but just in general. We know we had the rational function that had an asymptote at x equals 1 right here. And that graph looked like this and like this. And then we had our root function, which looked like this. Does have an intersection there. And we are looking for the value where these two graphs intersect each other. And that point right here was the ordered pair 2.466, comma 0.682. So our answer is, our solution is x equals 2.466,